Welcome everyone to Past Business Intelligence virtual chapter. Today's session is sponsored by Pragmatic Works, and without their sponsorship we won't be able to deliver this training for free, as well as providing prizes. I think today we have two actually, one from Pragmatic Works and one from Past Headquarters, as we actually, as the BI virtual chapter actually won the highest number of referrals, so we're able to pass that prize giveaway to you. To do that or to enter the prize giveaways, please complete the survey at the end of the session. Okay, so let's just get started with some news from Past Headquarters. Oh, firstly, Happy New Year, by the way. It's still, what's the date today? Over here in Australia, it's already 13th of January. Yeah. Anyway, so BI virtual chapter is not the only past virtual chapters that are available under the past governance. So if you'd like to know more about it, please go to SQLPast.org. I'm sure there will be at least more than one that you're interested in. And we do actually have other virtual chapter meetings throughout the month, including the ones for business analytics, and there's also another one for business intelligence too towards the end of the month. And if you don't already know, there is Past Business Analytics Conference held in April 20th to 22nd in Santa Clara, California. So if you're in the business analytics area, this might be something that you're interested in. And for more information, please go to pastbaconference.com. Another exciting conference that is coming to Europe is the SQLRally Nordic, and that happens on the March 2nd to 4th. And if you would like to register, you can use this code that is listed on the screen, Past Chapters 5. And yeah, so hopefully one of these days I'll be able to make it out there in the Nordic area for a SQL event. And upcoming SQL Saturdays are listed on the screen here, including the ones that I'll be attending and I'm helping organizing, which is SQL Saturday Melbourne on the February 7th. So hopefully we'll see you there. There are some pre-con sessions available as well. And if you'd like to volunteer for any parts of past, for example, for your user group or for virtual chapters, please don't hesitate to go to volunteer.sqlpast.org. A lot of the past groups are actually that we won't be able to deliver lots of these free seminars without your help from volunteers. And we do recognize volunteers as well. There are two awards. One is Outstanding Past Volunteer, and another one is Passion Award winner. So if you recognize someone who is actually have helped with the past community, please nominate them. That would be great. And if you'd like to stay involved, go to SQLPast.org. And if you're active on Twitter, follow us there too. Our SQL community is pretty active on Twitter. And our next session is on the 27th of January on SSI's internals and performance with David Peter Hansen. If you'd like to register, go to bi.sqlpast.org. There'll be more information about the session, as well as you can click on the registration URL there to register. Now, without further ado, we do have Marco Russo, who will be talking inside xVelocity in Memory Engine. And we do actually have a poll that I will push now while I transition the presenter mode to Marco. Marco, are you there?
Oh, yes. I was waiting for you to pass me the control, but this is the quick poll now.
Can you see the poll? Yeah,
sorry,
in progress. The poll should be in progress right now, so I'm just going to transition.
Okay. Sorry.
That's all right.
Okay, so thank you. So I should show my screen.
So I will close the poll in about maybe 30 seconds.
Okay. Now I understand. Sorry. I forgot that there was a polling before. So okay. So I think I can start introducing the session in the meantime, or we want to wait a few seconds.
Yeah.
Okay. So the session today is about the xVelocity memory engine, And the goal for this session is to explain how the engine works internally, how the compression is made, because this can be helpful to optimize the data model, consume less memory, and also optimize the performance of your models. As you will see, this notion is very important to any operation that you can do in designing a data model in Power Pivot or in Analysis Services Tabular. So I think I will have time, I hope, to show you a few examples and demos, even if the main most of the time we try to describe what happened in memory, even if we cannot actually show what is in memory, because it would be just bytes and bits, and we have to explain some concept like how the compression works. And so for this reason I have a few animated slides that will show you how the compression works and how we can improve the compression by preparing data in a certain way.
Okay, excellent. So we're just on 2 minutes on the poll, so I might just close the poll now.
Okay.
Okay. So we've got about 71% voted for Power Pivot for Excel and 65% on Analysis Services Tabular, which is pretty cool here. Let me just share that quickly so you can see.
Yes.
And I'll just hide that now, and then over to you, Marco.
Okay, how can I never used this. How can I see the result?
Oh, so I just shared the poll then. Can you see?
Not yet, because now I don't have the window.
Okay, I'll just leave it out to you then.
Okay, don't mind. So, okay. But more or less 1/3 is Power Pivot and 2/3 are Analysis Services, right?
Yeah, yeah.
Okay, good. Okay, no, but I think we can start at this point. So let me go back to the slide. And so as you see, this is my email. If you want to, if you have any question that I will not be able to answer during the session, please write me an email later. If you have any question, you can, I think you can get questions from attendees, right? And you can forward them to me.
Yes, I will raise the question when they're relevant to the slide.
Yes.
Yeah.
Perfect. Okay, so don't be shy. If you have question, send your question, and I will try to answer. And I will have also a Q&A time near the end of the session. So I'm a BI expert and consultant. I wrote several books about analysis services and Power Pivot, and we also wrote a new book about DAX, the DAX pattern, but you can find everything, I think, just visiting our website or my blog. You look for Marco Russo SQL BI blog, and you will easily find all this stuff. So before looking the agenda, I just want to explain more in detail what we are going to see. When you run a query to Analysis Services Tabular, you have two possible ways of resolving the query. One is direct query, and the other is the in-memory mode. In this session, we will consider only the in-memory mode, so this part of the architecture, which is the same and the only one that is used by Power Pivot. In Analysis Services Tabular, you also have the ability to translate any DAX query into a SQL query without storing any copy of the data in Analysis Services. We are not covering direct query in this session. This session is entirely dedicated to examine how Analysis Services and Power Pivot store data in the VertiPaq storage, which is a copy of the data retrieved from your data sources like SQL Server, Oracle, or whatever data source you get data from, and you have a copy of this data stored in memory in the VertiPaq storage engine. Now, just let me go to the next slide. Okay, so this is the only place where we focus our topic. So we have the in-memory mode, which is the one that we are considering in this session, and the in-memory mode is also the only one in analysis services that provides all the features of DAX and Tabular. In fact, if you use direct query, you have to avoid the usage of certain features in Tabular, like the calculated columns, and also certain DAX functions, like the time intelligence functions. But this is just a detail. Now, let's consider what is the topic, what are the topics that we will cover today. First of all, we will see how xVelocity stores data. Then we will take a look at how we can monitor and how we can measure how the data have been compressed in our data model. Then we will shortly describe a few basic optimization techniques that we can use in order to optimize the memory that we use for our data models, and of course a few best practices in data model design. So these are the topics that we'll cover in this hour. So the name of the session is xVelocity Memory Engine, and the xVelocity Memory Engine is the marketing name for what we are used to call VertiPaq. VertiPaq is the internal name of this technology, is the name that has been used since the development, and this is also still used today in all the profiler events that you can see when you debug your solution. So for this reason, I will use xVelocity or VertiPaq in the same way, fundamentally, with the same meaning. So xVelocity memory, or VertiPaq, is an in-memory database. So it is stored entirely in memory, based on the relational methodology. So we design a data model talking about tables, columns, and relationships. But the storage of these tables is not a row-oriented layout like we are used to in a relational database, in a traditional relational database. Now we have a column-oriented database. So the first question is, what is a column-oriented database? What is the difference between a row-oriented database and a column-oriented database? We can see an example starting with the description of a row storage layout. Consider a customer's table, like a table in Excel, for example. You have several columns and several rows. Every column has data of the same data type, usually, and in each row you have several values for each column. Now, the physical storage of this table in a row storage layout, like, for example, SQL Server or Oracle, is storing the data of each row together. So fundamentally, we put all the data of one row, all the values of the columns of a single row, in a contiguous area of memory or in a contiguous area of the storage of the disk, for example. SQL Server does not store data row by row, it stores data page by page. So it means that it allocates a fixed amount of disk, for example, and store in this area as more rows as it can. Which means that, for example, you have the first rows, the first 3 rows in a page in SQL Server. Then you have other 3 rows in another page, and so on. So fundamentally, regardless of the fact that you have pages or not, retrieving one row is an atomic operation in a row storage layout. And when you retrieve one row, you have access to all the values of all the columns of that row. Which means that if you have to sum the total of one column, in order to read one column, you have to read all the rows, because you fundamentally have to retrieve this page, this page, this page. And in terms of I/O operation, the number of I/O operation that you have to perform in order to retrieve all the values from one column is identical to the number of I/O operation that you would perform by retrieving 2, 3, or all the columns. For this reason, a database like SQL Server fundamentally improves the performance by creating a copy of the data in other tables that have a fewer number of columns. We call these tables indexes, and these indexes may also be sorted in a particular way so that it also improves the performance of retrieving a single specific value from the table. But in reality, when you have to sum the value of many rows in one column, then you have usually to perform a scan operation of a subset or all the rows of a table. And the presence of an index in SQL Server, for example, improves the performance of such operation, because you reduce the number of I/O operation, storing a higher number of rows into the same number of pages. So we know this structure very well because we are used to this structure, and we take for granted that every database should work in this way. But in reality, this is not true. A column-oriented layout, a columnar storage layout works in a different way. We want to store exactly the same table. From a logical point of view, we want to store the same data. But the physical layout of this data is completely different. Now, for a moment, imagine that we had to store this data on disk. We have an in-memory database, but for a moment, imagine that we have a columnar storage layout on disk. In this case, we would create one file for each column. And every file would be fundamentally a table that has only one column. If you think about this, when you have this structure, if you have to retrieve the row number 4, you have to do a high number of I/O operations, because you have to open this file, the ID, and you have to retrieve the 5th position in this file. Then you have to repeat the same operation for name, and so on for all the columns. So the number of I/O operations required to retrieve one row is correspondent to the number of columns that you have in the table, at least the number of columns that you have in the table, which is not particularly fast. However, if you have to sum the values in one column, you want to sum the total of the values of this column balanced due, it is much, much faster, because when you read one file, it is a contiguous area of disk. It is a sequential operation, and you will reduce the number of I/O operations to the minimal number to retrieve all these values. So having data in a contiguous area of disk improves the performance of the I/O. This is true also when these data are in memory. When you have this data in memory, you have to imagine that all the data of this column, of the ID column, for example, are stored in a contiguous area of memory, in an array in memory. You have an array of values for ID, another array for name, and another for address, and so on, for all the columns. So the contiguity of the data in RAM might seem a useless thing, but in reality it is very important because it improves the performance when you have to scan the entire column, because you have a better usage of the cache of the CPU, and this improves the performance a lot. So fundamentally, in terms of physical storage, we have the same data stored in a physical different way. And this data, of course, have pros, and this way of storing data has pros and cons. From a computational point of view, we have a quicker access to this data when we have to scan one column. However, when you have to retrieve the content of the entire row, we need time to retrieve all the values in all the columns, and we have to materialize the result in something that the user expects, because the user expects to see data row by row. Also, a program expects to retrieve data row by row. But the assumption is that the columnar storage layout is an advantage when usually most of the queries have to group data and to create aggregations of data. So the result will usually contain only a subset of the columns that you have in the raw data, and you have to aggregate this data by doing a sort of group by operation. The row storage layout provides a quicker access to a single row and provide also a quick way to not only read data but also to update and to insert data into the structure of a table. If you think about the columnar storage layout, adding one row is a nightmare because you have to open and change several arrays or several files on disk. So fundamentally, in the columnar storage layout, we usually do a lower number of I/O operations, but usually we spend some more CPU cycle in order to materialize the data. Now, by having only the columnar storage layout, usually we will not get a huge advantage. Even if the data are in memory, we still have to scan the entire array just to retrieve one value, or to retrieve all the occurrences of one value. For this reason, and also to reduce the footprint of the data in memory, the implementation of the VertiPaq storage engine not only uses a columnar storage layout in memory, not only stores all the data in memory, it also compresses data in memory. So the data is stored in a compressed way in memory, and it is uncompressed dynamically during the scan, but every query fundamentally scans data that are compressed in memory and doing a sort of uncompression during the scan. But we never have an uncompressed data, an uncompressed version of the data in memory unless we do a particular operation, which is the materialization that we will see later. So it is important to understand which algorithms are used to compress data by xVelocity. And there are two main algorithms, two main techniques that are used to do the compression. The first is run length encoding. Through run length encoding, fundamentally, contiguous rows in a table that have the same value can be represented in a different way. So instead of duplicating the same value in many contiguous columns, the values in this column are represented through a table that contains the value, the starting position, and the number of duplicated rows with the same value. So for example, if you have Q1 repeated 310 times starting from the first row, you simply have to store data in this way. And this is automatically done by VertiPaq, of course. Now, this situation is the optimal situation. We have a column that is sorted by using values of this column. So fundamentally, we see all the rows with Q1, then all the rows with Q2, and so on. And in this way, we will have only 4 rows here. However, if we sort a table by the quarter column, we cannot have an optimal sort order into another column. So for example, the column product ID will have 1, 2, but will repeat 1, 2, and other numbers when we start the Q2, for example. However, by trying to apply the run length encoding to this column, we may figure out that the total size of the resulting table is smaller than the original column. So if the size in memory of this structure is lower than the size in memory of the original column, then this is the way these data are stored in memory. However, we may have a column that never has duplicated data across contiguous rows. In this case, the run length encoding will be more expensive and it is not used. So the column is stored in this way. As you can understand, retrieving one column or retrieving the values or the number of occurrences of a value in the table requires a scan of the structure and some logic that requires some CPU cycle. But modern CPU have very high clock speed compared to the time required to access RAM. So if we can reduce the number of data that we have to retrieve from the RAM to the CPU, even if we spend some more CPU cycle, usually the resulting performance is better. So run length encoding compression is applied only when the size of the compressed data is smaller than the original data. In order to optimize the run length encoding, when VertiPaq retrieves data from the data source, it tries to sort data by different columns, finding the optimal sort order of the data column by column in order to obtain the best size of the compressed data. So in this case, having only 3 columns, chances are that the engine will easily retrieve the optimal sort order, the optimal combination of columns to sort by. However, if you have many columns, this operation could require more time. There are a few parameters in analysis services that cannot be set in Power Pivot that could enlarge the time allowed to find the optimal sort order if you want to do fine-tuning for this stuff. However, usually the engine does a good job, but consider that if you provide sorted data to the engine, the first attempt will be the optimal one, and you can reduce the time allowed to the engine to find the best compression in order to do the optimal compression. The second algorithm is the dictionary encoding. The dictionary encoding is very simple. Fundamentally, there is a dictionary that contains all the unique values of a column, and the column itself references the dictionary using an integer value, and that is the index of the value in the dictionary. Now, an important thing to consider is that the number of bits used by this index is the minimal number of bits required to retrieve, to index the elements that are in the dictionary. So if you have a column that only has 4 values, each value requires only 2 bits, because the dictionary could be very large, but in reality you only need, for example, 16 bits if your table is up to 65,000 rows or something like that. And reducing the number of unique values in a column also reduces this dictionary and is also a very good compression technique. The two techniques are combined together, so the run length encoding and the dictionary work together in order to optimize the compression at the maximum level. But as you can understand, the number of unique values in a column is very important in order to optimize the compression rate. Having a higher compression means reducing the amount of RAM that the CPU has to read during each scan, and this improves the performance of any query. This is very important. So the dictionary encoding is automatically handled by the engine. There is only one exception. The dictionary encoding is not used if your column is an integer value that has a range of values that is contiguous. And in that case, it could be compressed also without the dictionary. For example, if you only have numbers between 0 and 15, they will be compressed in 4 bits and without any dictionary. But if you have a floating point, if you have a money data type, so any other number that is not integer, there will be always a dictionary for your column. So the compression comes from the column store, the dictionary encoding, and the run length encoding. And usually we can obtain a compression factor around 7, 8, also 10, which means that if I have 100 gigabytes of uncompressed data without indexes in SQL Server, the typical compression we obtain in Tabular is we store the same data in 10 gigabytes. However, yep.
Sorry, we do have a question here. I thought I might just ask.
Yes, of course, of course.
So for the RLE, when VertiPaq is trying to find the optimal sort order, is it trying to sort only within each segment, or can it sort across segments in a partition?
Each segment is a different has a different technique. We will we don't have time to explain the compression in detail, but fundamentally every I will talk about the segmentation in the next slide. So I can already let me go to the next slide. When you process a table, the table is split into different segments, which means that if you have a table that has, for example, 100 million rows, the engine reads one segment in memory of uncompressed data and tries to compress this data. This means that in this segment, the list of unique values is detected in order to build the dictionary, and the optimal sort order is tried within the segment. In reality, we have the read of two segments at the beginning of the scan of a table, and if I remember well, the reason for that is also to better analyze the sort order. I'm not sure about the sort order is changed or not for every segment. I'm not sure about that. I should review because it's not documented this, and we have to figure out doing some tests of how it works. But I'm pretty sure of one thing. If you have a dictionary that is very large, but in a segment you have only a subset of the dictionary used, the index used to map the values in the dictionary is local to the segment. So for example, if you have the date column that has many dates, but you sorted your data by date and you are processing the first segment, chances are that you have only 1, 2, or 3, or 4 dates in the current segment, and this reduces the number of bits used to store each value of the date column, even if the dates that you have in the date table is 1,000, for example. And this compression is also very important. I'm sorry that I don't remember, but I'm not sure that we ever seen how this works internally, because I'm not sure Microsoft documented this. Okay, so I was saying about the compression rate. I go back one slide. And a factor 10 of compression is usually a good compression ratio, but by carefully choosing the number of unique values that you have in the columns, you may reach much higher compression. We have seen compression rates of 100 times. So from a 100 gigabyte database, uncompressed database in SQL, we obtained a 1 gigabyte database in Analysis Services Tabular. Now, talking about segments, we can change the segment size in Analysis Services. We cannot change the segment size in Power Pivot. Why Power Pivot has a lower segment size? Because of the RAM. available. Remember, you have to read all the uncompressed rows in memory in order to perform the compression. And if you have one row that is 1 kilobyte large, 1 million rows means 1 gigabyte. And you know, Power Pivot in 32-bit will not be able to handle that. If you have analysis services, this is the same. And so having a very large fact table, for example, a very large row in a table means that you need a large buffer just to read data and do the compression. You may want to reduce this number in analysis services, or you may want to enlarge this number in order to improve the compression rate, especially if your row size is not so large and you have a lot of rows. For example, in tables with billion of rows, and of course with an average row size of a few tens of bytes, we increased this number and we improved the compression rate in a very, very important way. So how can we predict how much RAM we will need for our data model? This is a very hard question because the memory usage depends on the number of columns, on the cardinality of each column, on the data type, and on the number of rows, of course. But the cardinality of each column is much, much more important of the data type. I don't care if a column has a string of 20 bytes, 20 characters or more compared to an integer. I care about the number of unique values in a column. I'm sure that storing a string long 100 characters in a 1 billion rows table is very inexpensive if we have only 2 different values for that column. Whereas an integer value that has 1 million of unique values is a very expensive column because it cannot be compressed so much with the compression algorithms that we have seen before. Of course, the size of the string can be important for the dictionary size, especially when you have a large number of unique values in that column. It's hard to find a formula to predict how much memory we will need. Usually, we test a real sample of data. We test with 1 million rows, then 2 million rows, then 3 million rows, and we try to predict the growth curve by sampling different volume of data. Just because it is really too complex to make a prediction of the memory that we will need when our model will grow, because we have to predict not only how many rows we will have, but also whether the columns will increase the number of unique values or not. So let me go to the next slide. What about the memory used during the query? Usually a query in an MDX or DAX does not require much memory because the engine only reads data and does not have to write data in memory. However, there are complex queries that may require more memory. And this happens especially when the query plan generates internal materialization of data. What does it mean? For example, we have, oh, sorry, I was checking a couple of things. We have this possible problem. Let me explain the problem of the materialization by showing you an example using a SQL query over a columnar storage database. We don't have actually the ability to do that in the real world, but imagine that we have a table stored in this way, column by column, and this SQL query. With early materialization, we have fundamentally the creation of a table in memory that contains the actual row of the table that we want to analyze for our SQL query. So fundamentally, by starting from the columns that are involved in this query, even if these columns belong to different tables, it doesn't matter, but fundamentally we build in memory all the data. And as you see now, we have uncompressed data here, whereas the original column could have been compressed. As we have seen, we would have here the dictionary, the run length encoding, and so on. So the size required for this table could be larger than the sum of the sides of these columns. When this happens, we may need much more memory than the memory of the original table. Then the where condition is applied, the table is reduced, the projection is applied, and the group operation is executed. So we have at the end our result, but this could require a lot of RAM. Usually this doesn't happen. What we should have is late materialization. So all the operation, the where condition, for example, is applied straight to the original columns, and we consider a bitmap index over these columns, and the result of this bitmap index is applied to the other columns. So the materialization can be applied only at the very late, very late in the process of building the result, so that only when we have to do the group by, the materialization happens. Now, if you consider the amount of memory required to create this temporary table in memory, and this temporary table is created in an uncompressed way, it is much smaller than the one that we have seen before. Now, for simple queries, we usually have late materialization. However, if you experienced very bad performance in using a tabular model or a power pivot model, may be that you experienced an early materialization. And the materialization can happen when you have complex joins, complex iterators, or DAX formulas written in a non-optimal way. So let me show you what can happen when this when you have this situation. So in this case, I'm using here DAX Studio, which is a tool that allows me to create DAX queries and navigating over tabular models. This is a free tool that you can easily download and is provided with source code on Codeplex. And this tool simply allows me to write a query and run the query. I can see the result here, and as you see, we have 10,000 as a result of this query. What I have in reality is a table that is called numbers, and this table numbers has 100 million of rows. In fact, if I put in count rows numbers, I can run only this query, and you can see that I have 100 million of rows. Just to check, this is the number of rows that I have in my table. Now, the number of unique values, so the distinct count of the column numbers num1, correspond to 10,000. Let me check. Oh, I have too many close parentheses. Run again. And this is the number that I have here. So fundamentally, in this table, I have all the combinations of the numbers between 1 and 10,000. In fact, also num2 is a column that has the same number. Now, up to now, you have seen that any query had a duration of close to 0 seconds, fundamentally. Also this time, I can run this again, as you see, 5 milliseconds. So it's very, very fast. However, I can try an intentionally bad performing query by just, for example, doing a count rows of all of this column, comma, this other column. And if I do that, as you see, the query started, and now what is happening? In the meantime, we can see that the performance are, all the cores are running 100%, and the memory size is increasing. We are experiencing materialization. We are generating in memory all the combinations of all the values of these two columns, and this is a very expensive operation. Now I cancel this query because I don't want to go out of memory during a demo, but as you have seen, we moved from a few milliseconds to many, many, many seconds. Probably it requires 1 minute, and it requires also a few gigabytes of RAM just to materialize 100 million of rows where we have 2 numbers in each row, and there is an overhead for each row materialized in memory. So this is not what we want to happen. So when you find that you see memory increasing and a slow performing query, you are experiencing materialization. When this happens, the solution is usually changing and optimizing the DAX code, writing the same expression in another way. Not something that we can handle in this session, of course, but just to making you aware of what could happen when materialization happens is important. Now, we can also analyze how the data have been stored in memory. We have a few data management views that provide us a few information. For example, the discover object memory usage is a query that provides us important information about what is the usage of the memory made by our models. So discover memory usage, I think this one, or object memory usage probably, this other one. So let me just copy this. As you see, we have these queries are ready to use in DAX Studio. I can run this query and I can see here the result. This result contains a lot of information that provide us the memory used by each object, each column, each segment, each index that we have in memory. Now, reading the data in this way is not very easy. So a better way is to use the BIS memory report analyzer, which is an Excel file with a Power Pivot model that fundamentally reads this table. Let me show you how this model works. We fundamentally have a query that send the same DMV query to the analysis services tabular instance I have on my machine and populates this table. In this table, we also have a few calculated columns that will generate information for a hierarchy and a few measures that sum the data that we want to show in the pivot table. And this makes the reading of our information much easier. For example, we see that we have 13 gigabytes used by, almost 14 gigabytes used by our databases in my tabular instance, but 98% of the space is used by a single database. And this database that has a few, if I remember, we have 4 billion rows, and we have 13 gigabytes for 4 billion rows. As you see, the number of rows is the same for every column, but every column has a different amount of RAM used. You see that the dim date, ID date, has a very low number because it has a very high compression rate, whereas ID time has a higher number of, as a larger space, a larger amount of RAM used. Why? Because you see, we have in this table we have data about date, time, channel, television channel, description of the people that watch the particular program on TV, and the time is has a resolution down to the second and cannot be compressed, because if you compress by date, then the time grows, and then restart. So we don't have an optimal sort order for the time. And for this reason, we have this high number here. Another reason for having a high number here is because you have a high number of unique values. Now, this table is very, very optimized, but if you take a look at AdventureWorks, you can see here that in AdventureWorks, in the product inventory table, if you go down to the columns, you can see that the larger column is probably the column that has something close to the primary key of the column. So if you have a primary key in a column, is usually the most expensive column of the table. So you can read this data using this tool. This tool can be downloaded for free from this URL. So if you look for Casper de Jong BISM memory report, you will download this workbook. Now, how can we reduce the memory used by our model? Fundamentally by reducing, for example, the dictionary, by reducing the number of unique values that you have in a column. So, for example, if you have a date time, if you are reading the log of a web site and you have a timestamp in a column, split this column into two columns. In one column you will store only the date, and in the other column only the time. Moreover, if you have the time with the precision of the milliseconds, you probably want to round the precision close down to the closest second or minute, depending on the analysis that you will have to do. The lower the number of unique values, the better. So if you don't have to do analysis at the second level, just keep the minute level. We could also truncate the floating point values by just reducing the number of unique values you have. For example, if you have the temperature stored with 3 decimals, and you know that, oh, 1 decimal is enough for our analysis, you could just round the number, removing the noise of the small decimal points that you don't want to store, just because in this way you reduce the number of unique values. This is not possible, of course, if you have money, usually. Another good technique is removing columns. If you have a column that has a lot of unique values and you never use this column, just remove it. If you have a column that has the primary key of a fact table, we usually remove the primary key of a fact table from a tabular model, because we usually never use that column during a query. Junk dimension, if you are used to creating junk dimension in order to reduce the number of columns that you have in the fact table, for example, be careful, because 5 columns in a fact table that have a low number of unique values could be better than trying to normalize everything into a junk dimension. If you know Kimball, if you know junk dimension, be careful. If you just look at the compression rate, it could be not a good idea using junk dimension when you have just a flag true false in a fact table. Storing them as original flags could be better. But of course, it could be not the optimal thing for other reasons. What about the ID that we want to use? For example, you have the invoice ID that you want to keep in the data model, for example, for drill through in a pivot table. In this case, the invoice ID could be the more expensive column in a fact table, and for this reason, we suggested to split this column. To split this column into 2 columns. For example, if you have a number, imagine that you have transaction ID, which is a number that is around hundreds of millions. You may store this number into 2 numbers, creating 2 columns where you will have many conflicting values between different rows. We store the same information just in 2 columns, but we reduce the size of memory used. You may wonder whether this works, this is important or not, but this is just an example. The original table that I shown you before, the numbers column, if I stored the number column, the numbers table by storing 1 column with all the numbers between 1 and 100 millions, I would have stored almost 3 gigabytes. I would have needed almost 3 gigabytes of RAM. However, with the design we used, by using 2 columns with the numbers between 1 and 10,000, we reduced more than 90%. We saved more than 90% of the RAM. We are lower than 200 megabytes in this way. This could be reduced more by splitting the columns more, but usually it does not worth the effort. It is better also for usability reasons to stop at the first step. This could be a very important optimization technique that moves us to another point, which is which columns should you store in a fact table? For example, imagine that you have this fact table. The columns that contains the foreign key, order ID, product ID, are required. You need them to create relationships. The columns that have a small number of unique values are stored again, but if you have a column like sales amount, consider this. Sales amount can be obtained row by row by multiplying quantity by price. So I could avoid storing sales amount, and I can obtain sales amount by creating a DAX measure that multiply price by quantity row by row at query time. Believe it or not, this is much, much better for both performance at query time and memory size, because you compress data more. It is the same principle of the column split that we have seen before. We store the same information in a higher number of columns, but by compressing data more, because we have a higher number of identical values in quantity and price. Just think about this. How many unique values you have in quantity, how many unique values you have in price, how many unique values you have in sales amount. Do all the tests that you want on your data, you will find that usually sales amount is 1, 2, or 3 order of magnitude more in terms of unique values than quantity or price. And the compression that you obtain is much higher. So this is a very important optimization technique that impacts in the way you design your data model. So if you wonder what is the gain that we can obtain, well, we have a few measures. In a table that has 4 billion rows, on a server that made a scan with a cold cache, so no cache, no data prepared, the first query ran in 13 seconds just to do a sum of this column. When we stored the column into 2 columns, so instead of sales amount, we stored the quantity and price, for the same table, 4 billion rows, we reduced the time from 13 seconds and 9 gigabytes in RAM to 3 seconds and a much smaller, around 2 gigabytes of RAM size. So we fundamentally, reducing the RAM, we also reduced the query time. We used a more complex calculation. We are spending more CPU, but the issue in the time is not the CPU speed, is the RAM speed. The reason why we spent 13 seconds is because it is the time required to move 9 gigabytes of RAM to the CPU to do the math. If we reduce the amount of RAM transferred in these large tables, we improve the performance every single time. So we have seen that the Columnar database is very different. The dictionary size is important. Is important for 2 reasons: because of the size to store the dictionary, and because of the compression that would be certainly better if the number of unique values in a column is smaller. The segment size could be important in very large tables, especially to increase the compression if you have enough RAM to afford this increasing. And the segments are also important for the parallelization of the query. When you run a query, you have 1 thread per segment. And so when you increase the segment size, you also decrease the parallelization. But this is a good thing when you have 4 billion rows. You may want to increase the segment size just to avoid having too many different threads running, and you use in a better way the resources that you have available. So thank you very much. I think I have 2 minutes for the questions. I don't know if there are questions.
Yes, there are a few questions. So yep. I'll start with one. Okay, so one of the questions is, we are seeing performance issues with filters in Excel against dimensions in our tabular model, about 200,000 rows and 20 columns wide. Curious if you have seen issues like this before and if you had ideas on how to fix it.
No, this is a low number. 200,000 is not a high number of rows or values. Usually we see degradation of performance, especially when you have more than 2 million of unique values in a column, regardless of the size of the table. And when this happens, there are possible optimization, but fundamentally, if you are experiencing bad performance with this amount of data, probably the problem is more, you have to look into the DAX code that you wrote. Is probably not a question of compression, but a question of how you create the model, how you write the DAX measure.
Okay. We've got 2 more questions. So one of them is, where can we read more information about dictionary encoding specific to Microsoft's implementation and early versus late materialization as it applies to Tabular?
Okay, I think we have, there are a couple of things. There is a white paper, and just looking, let me check, because we have a white paper about, let me, I'm checking this, because on SQLBI.com we have, okay, this white paper could be useful. This is a comparison between VertiPaq and Column Store, and it contains also a few information about the internal implementation of VertiPaq. You should take a look for, there is a, let me check, there is a Microsoft Research white paper, Columnar database, which contains a very detailed description of the implementation of this. So this is about the SQL Server column store index. However, there is another one. No, it is not published here. Most of the concepts that are in VertiPaq are also described in this white paper, however, which is available here. As you see, announcement to SQL Server column store. I think there was a former white paper, always from Microsoft Research. It was just not in the query result. If you look in Research Microsoft.com website, there should be some other white paper from the Microsoft Research team that developed the first engine for this.
Okay.
I think these are the only published information about this thing.
Okay. Right. So we've got a couple more, if that's okay.
Yes,
do you see a difference in normalized versus denormalized dimensions? I'm assuming performance difference, maybe?
Yeah. Assuming that, okay, from a purely theoretical point of view, a single table would have a better compression. But in the real world, having a single table has many other side effects and is not good for many other reasons. So a good idea is designing a star schema and not a snowflake schema. The star schema is the best balance between having relationships between tables, because relationships are expensive also for the VertiPaq engine. But having a normalization within a dimension is usually something that does not worth the effort. So usually creating a snowflake does not provide you any performance advantage. Usually it lowers the performance, usually. And you spend more RAM for storing the relationship. So the good balance is the star schema.
Okay. And I think one last question for the day, and I think this is the most common one that people ask whenever we talk about Tabular. Will VertiPaq eventually replace analysis services multidimensional?
This is a hard question, because in terms of, I don't know what Microsoft will do in 10 years. I know that Microsoft will not remove multidimensional from the market and will not remove MDX as a query language. This is for sure, because there are just too many products around, also by Microsoft, like Excel, that are completely based on this on MDX language. That said, I would like, but it is just my desire, I would like to be able to use the VertiPaq engine with a multidimensional model. And in another case, I would like also to do the opposite. But it would be interesting to see a multidimensional implementation based on the VertiPaq engine instead of the MOLAP engine. It is just my desire, but this will be very good for a number of scenarios. These are very different models. I think that 80% of the data models could be implemented in both multidimensional and the tabular in a successful way. There are a few other conditions where tabular is much better and others in which multidimensional is much better. And these conditions could be very important for certain companies, also big enterprises. So I suppose that we will still see both engines available for a very long time.
Right. Okay, thank you for the answers, Marco, and thank you so much for presenting. I think that's all with the questions. And just letting everyone know that this session is recorded and will be uploaded to our YouTube account, which is youtube.com/user/pastbivc. And again, thank you for Pragmatic Works for sponsoring the session today. Thanks, everyone. Thank you, Marco.
Thank you very much. Thank you. Bye-bye.